Here we have an example of control chart methodology, and it's in a very sort of unusual area of application, just to show that it can go beyond that. We're looking at the extent of Arctic sea ice. Over the last decades, we have been concerned that the Arctic sea ice may be disappearing. And that's a very important problem because, well, our poor polar bears may become extinct, and that would be absolutely terrible. We may have increased shipping traffic on the Northwest Passage, including cruise ships. I've actually heard of a couple of cruise ships. Increased commercial activities like oil drilling and increased tensions with Canada's neighbors, right? Because this area up there is getting more commercialized. Can we detect a shift using process control methodology in this unusual application? Well, we do have data over time, or order data, so it does apply. And what I found is I found daily data from 1978 and onwards. And if I plot this all here, the daily data, you can see there is a huge seasonality between summer and winter. In the summer, there being not much sea ice, and in the winter, there being more, right? When it's cold, makes sense. So, and the seasonality, the very strong seasonality clearly overwhelms any trend that there may be in here. So, since we're looking at control chart methodology and looking to make that work in this example, I'm going to first look at an excerpt of the seasonality. Here I have 3 years, and you can see that roughly in September, we reach the lowest extent. Well, it is true. I don't have enough labels here that you can see it's exactly December, but September, but it's true. So what we do is to get rid of the seasonality. I take the average value in each September and plot that over time. So what you see are the September averages over time. And I got rid of all the other data. So we don't have to worry about seasonality anymore. We're just looking at September. All right, now we can see a clear trend here just visually, and let's see whether the control chart methodologies can detect that and how. I have to figure out what the variation is, and I'm establishing the control limits based on the first 5 observations. This is arbitrary, 1979 to 1983, but you somehow have to have an in-control process or something to get it started, right? So then I computed the Shewhart 3 sigma control chart limits, which are also plotted. And you can see for the first time, we are going out of control here. This point is out of control, and we are down here at 1991. So we are starting this after the 5th point. So we are starting in 84, and in 91, we can detect we are out of control. And then if one were to continue, of course, you see it goes more out of control, but we detect it here. Okay, so let's see what happens for the CUSUM. I chose k equals 0.5 because we had seen in the previous segment that the average run length until we get a false alarm is the same using this parameter as compared to the 3 sigma limits on the Shewhart chart. So we're making them comparable. So for the adjusted CUSUM with the control limits, we get 2 curves, one to test for a score for an increase in mean, one for a decrease. And the increase in mean stays at the bottom here, never gets any air. Well, because there is no increase, right? So there's no evidence for an increase, so that makes sense. And for the score for a decrease in mean, that goes up and up and up and up until it gets the threshold. And then here we would raise an alarm. And so I said there's an alarm in 2000. So this must be just a tiny bit above the threshold or just reach the threshold. So we have an alarm here. This is 9 years later than what we found with the Shewhart chart. A little bit surprising, but there's still an alarm, and then it continues going up and up and up. So the EWMA, again, with an alpha value that corresponds to the same average run length for getting the first false alarm. also has control limits. And here we're getting out of control this is in control in this point, which is 1992. So it's 1 year after the Shewhart out of control one. Of course, with the benefit on hindsight and knowing exactly what you want, I can tweak the alpha and get different control limits here, wider or smaller, depending what I want. The graph changes a bit, and then the results changed a bit. But as I said, to make it comparable, I kept it all at the same level with the same false alarm average run length. Okay, so we know that Shewhart charts don't work well for detecting small shifts. But here, the Shewhart chart actually was the best one, meaning it raised the alarm first. So that means we either have a large shift or an ongoing drift. And in this case, we probably have, at least in this data set, we have probably an ongoing drift. And the performance of CUSUM and EWMA depends on the tuning parameters, which we set on the desired average run length for no signal, no false alarm. Okie dokie. So, yeah, that concludes this segment.